Welcome to EDU AMP. This is a GCSE physics lesson and it's all about atmospheric pressure. What I hope you'll be able to do at the end of this lesson is describe a model to explain atmospheric pressure and explain why atmospheric pressure decreases with height. Now, in the previous part of GCSE physics, you may or may not have tackled pressure and seen a pressure equation that pressure times volume equals a constant. So some of this may not be brand new to you, but it's a good opportunity to recap. So this simulation here nicely shows you what creates air pressure. So what you've got here is a container. Don't worry about the little man here, he's used for something else, but what you've got is a container and it's empty, it's a vacuum, there's nothing there whatsoever. And here you've got a super duper pressure sensor. It's measuring ATM, and that is actually atmospheric pressure. So basically it's on zero at the moment because nothing's there at all. So what you can do is pump in some air particles. Now, when you pump the air particles in, you probably notice I'm starting to get a pressure reading. And the pressure has been detected, and it's been detected because these particles are creating air pressure. Well, why are they creating air pressure? Well, if you look at these particles, that you should know that particles in a gas are quite far apart and they're moving very quickly. Hence, they start hitting the walls of this container here. Now, if they hit the wall of the container, they then are going to exert a force. And because they exert a force over an area, pressure equals force divided by area. Hence, we start getting pressure. Now, don't worry too much about the units at the moment, but what we're picking up is about 0.3 ATM. Now, if I pump in more air, doesn't this make sense? I've now got more air particles. Once I have more particles hitting the wall, if more particles hit the wall, I'm going to have a bigger force. If I've got a bigger force, I'm going to have a bigger pressure. And you see now it's gone right from about 0.3 up to 1.6, 1.7. So this is why we get atmospheric pressure. Now, to go with that is this a diagram showing you atmospheric pressure. And what we've got here is I've got a balloon. I've got the air particles there inside the balloon, and these particles are hitting the wall, creating this pressure. On the outside, I've also got the air particles. They're hitting the wall. So therefore, what is happening is you've got the atmospheric pressure inside due to the air particles, and then inside this balloon, I've then got pressure pushing out, and that pressure pushing out is all due to the helium particles moving around. Now, if this balloon's staying at the same shape, this must mean I have balanced forces. In other words, the outside pressure and the inside pressure must be the same. Now, they can ask you to go in keywords to explain why you get air pressure, and these are the key words you need to use. You've got to start talking about the gas particles. And these gas particles could be all the air particles on the outside here. And what they're going to do is they're going to collide, or you can use the word hit. Okay, and I'm going to call this the balloon wall. Hit that wall, and therefore they're going to create a force. And they create that force over an area, and therefore this creates something called atmospheric pressure. And you've got to be able to use keywords in exam questions to make sure you answer the question correctly. So it's getting these keywords in. In other words, you've got to get in the fact gas particles collide, hit the wall, create a force over an area, and that's going to create atmospheric pressure. Now, this is a cool trick you can do at home. I advise you to do it at home over a sink because it can go completely wrong. I'm hoping to get it to appear here. Oh, wrong one. Here's the link here. And it's called the famous glass trick. Now, what you've got here, or the upside down trick, is you've got a glass full of water. And you simply have got here, an advert appearing, is going to be a piece of card. Now all you do is place the piece of card over the top, and then you turn it upside down. Very carefully take your hand off, and lo and behold, the paper or the card stays there. Cool trick. Now, if you get a seal broken there at all, you will end up having water absolutely everywhere, hence do it over the sink. Okay, now why this happens is, I'm going to get a little diagram here, try and get my rectangle out. Here I'm going to have the glass like this. And here underneath, you're going to have simply your piece of card, which is going to be along here. Oh, didn't draw a line. Come back here, all's forgiven. And you've got your card along the bottom here. Now, you've got water inside here. I know it's orange, but there you go. You've got water inside here, and that water inside is going to create a force going downwards, and it's going to be the weight of the water, all due to gravity. Now, that acts down. It then makes sense that you must have a force acting upwards, and that force must balance the force downwards, otherwise the water fall out. Now, this is created on the bottom from atmospheric pressure. And that atmospheric pressure is acting every single direction, but here on a card, it must be pushing it up. Okay, it's acting here as well, but it's pushing it upwards here on that card and stopping the water fall down. And it starts showing you how big atmospheric pressure is. It is about roughly 100,000 newtons per meter squared, which using the other units is going to be 100 kilopascals. Now it will vary. Some days it was going to be 990 kilopascals, sometimes 104, 105. Today's a nice sunny blue sky day, and it's probably going to be high pressure. And you may hear about this in the weather, they've got high or low pressure. So this is a rough average one, but it does change a little bit. But the atmospheric pressure is big enough to stop that water falling out. Now, I've explained to you what creates atmospheric pressure. There's a really cool class experiment you can do. And to do this, I'm going to show you a lovely smiley can. What you do is get any old drinks can, and you put about this much water on the bottom here. Then, grabbing hold of his red pen, use a Bunsen burner and heat it. And what you do then is you start boiling this water, and the water then will start to evaporate, and you start producing steam, which you can see coming out. And I'm going to use a black pen, you can see a bit better. And you then got lots of steam in this area here, which I'm wiggling my lines in, above the water here. So the steam starts rising. Now by the side, what you do is have a beaker like this. And in that beaker, what you do is you then put in cold water. Now the idea is you boil this water using steam for about a good 2-3 minutes. Then what you do is you take this can and very quickly you plunge it straight into the water like this. Now, if you bung it into the water going across like this here, when you put the can in, the can crushes. And I'll show you crushing because I did this in my kitchen. And this is a cool little video. No. Here's your can. And I'm boiling it using a gas stove. And I'm producing steam coming out here. And I've been boiling about 2 minutes. And yes, it'll go a very funny sound because of it in slow mode. I'm going to take the can and I'll lift the can, and then what I'm going to do is drop it vertically into the water. Here it goes. Now, there's a lot of steam in here, but as soon as it reaches the water, it's going to condense it, cools down the steam, and watch this can crushes in seconds. Now, that is all due to atmospheric pressure. Now, the reason why it happens is I'm going to draw another can over here, well, here, the side here. Let me get my arrows better in. Now, there's going to be your can, and you've got a tiny little hole here. Is when you're boiling the water, you basically, in normal conditions, you've got the pressure acting outside and the pressure acting inside, which are going to be equal. But what you're doing is you're producing a lot of steam here. When you put it into the cold water, you're going to condense all that steam. So suddenly you've got a lot less particles inside than you had outside. So in other words, then it doesn't quite go down to this of 0, but the inside pressure becomes a lot smaller, pushing out. Therefore, your outside pressure is going to be greater than your inside pressure. Hence, what you're going to have then is you're going to have unbalanced forces. And if you've got unbalanced forces, therefore the can will crush, and it crushes inwards. It's a really cool experiment you can do. Now, I've now explained to you what creates atmospheric pressure. Lastly, you need to know why is air pressure decreased with height. So if you went, for example, went to top of Mount Everest, you would find atmospheric pressure a lot less than it is on the surface of the Earth. Now, on the surface of the Earth, as I mentioned before, it's about 100,000 newtons per meter squared, but it does decrease with height going upwards. Well, why? Well, if you look very carefully here, you can see lots and lots of air particles. Do you notice at the top there's less air particles around because the density of all the air, or less particles, decreases? Doesn't that make sense? There's going to be less force, i.e. less collisions of these particles hitting the walls. Therefore, that makes sense. Then the pressure has to go down. When you're lower down towards the surface of the Earth, you can see here now, the density is going to be greater because you've got more particles there. Therefore, the pressure must increase. You can also look at it and the idea, the fact you've got more weight of air above you, therefore greater force, therefore the pressure increases. Very similar to when you think if you had in liquid, that the fact in liquid water, pressure increases with depth. Therefore, what we did is beforehand, you had your pressure equals height multiplied by your density multiplied by gravity. Therefore, if you've got a greater weight above you, you're going to have a greater pressure, very similar to liquid pressure. So what I've done for you is I've described a model to explain atmospheric pressure, and also what I've done is I've explained why atmospheric pressure decreases with height. Hope you enjoy the video.